3D object detection responsible for providing precise 3D bounding boxes of surrounding objects is an essential environmental perception task in autonomous driving. Recently, relying on the accurate depth measurements of LiDAR-based detectors have achieved superior performance. Several intrinsic deficiencies of the LiDAR system such as high cost and sensitivity to adverse weather conditions inevitably impose limitations on the applications of these methods. In contrast, camera sensors are more economical, robust in rain and snow, and feasible to satisfy strict vehicle regulations. According to ways of obtaining 3D information, monocular 3D object detectors can be roughly divided into three groups: pseudo-LiDAR, 2D/3D geometry constraint and keypoint-based methods. Pseudo-LiDAR-related methods acquire depth image using the existing monocular depth estimation algorithm, transform the acquired depth image to pseudo-LiDAR point cloud, which can be fed to LiDAR-based 3D object detectors. However, these methods usually suffer from poor efficiency due to the additional depth estimation module. Other methods based on 2D/3D geometry constraint translation information on the basis of the geometric relationship between 2D and 3D properties on the image plane. Due to their sensitivity to inaccurate prior properties such as 2D boxes, these methods are difficult to achieve both high accuracy and low latency. Compared with methods in other groups, detectors in the keypoint-based group have achieved great speed-accuracy balance and thus are more appropriate for autonomous driving applications. However, it is still far from satisfying the accuracy requirements for the safe environmental perception of autonomous vehicles. In this paper, we aim to improve the accuracy of keypoint-based methods and meanwhile strengthen their speed advantage. Here we introduce the major structure of keypoint-based monocular 3D object detector. As shown in Figure 1, the whole framework can be divided into backbone, detection head and post-process. The backbone network consists of an encoder and a decoder. The encoder extracts high-dimensional feature RGB image. The decoder upsamples the bottleneck features by 3D convolutional layers. The detection head consists of a keypoint branch and a regression branch. The keypoint branch predicts the existence probability and class of an object at each pixel. The regression branch predicts metric parameters of 3D bounding box. The post-process contains a top K process and a decoding process. The top K operation is applied on the heat map to get a certain amount of candidate keypoints. The decoding process is applied to the 3D information sampled from the regression map via the pixel indices to obtain the final 3D bounding boxes. In the feature hierarchical layers of the backbone network, the high-resolution feature maps possessing more accurately localized features and smaller receptive fields are adept at detecting small-scale objects. Conversely, the low-resolution maps providing stronger high-level semantics and larger receptive fields are appropriate for the objects in a large scale. For most keypoint-based detectors, the detection heads are applied on the largest scale feature maps as shown in Figure 1. On account of the deficiency of multi-scale information on a single feature map, it is challenging for these detectors to cover all objects within a range of scales and distances. Therefore, taking full advantage of multi-scale features in detection head is an effective way to improve the performance of keypoint-based detectors. In this paper, we present a class of lightweight feature pyramid network called LightFPN. The improved frame integrating our proposed LightFPN module is shown in Figure 2. In terms of the data flow, the newly designed regression branch with LightFPN module can be divided into keypoint proposal phase, feature fusion phase and regression phase. In the first phase, candidate keypoints expressed as classes and pixel indices are obtained via a top K operation applied on the heat map. In the feature fusion phase, based on the proportionate relationship of the pixel indices on different feature maps, We can get the pixel indices of candidate keypoints on the other two feature maps with 1/8 and 1/16 resolution of the input image by multiplying the previous pixel indices with 1/2 and respectively. Then, three groups of features with the same shape K plus D are sampled from the feature maps with 1/4, 1/8 and 1/16 resolution of the input image via the above three sets of pixel indices. Finally, the sampled features are concatenated together to create the embedding features with the shape of K plus 3D. In the regression phase, the embedding features are fed to a 1-by-1 convolutional layer to predict the geometric parameters related to 3D bounding box. Furthermore, owing to the independence between keypoint branch and regression branch in the training phase, there is a misalignment between the classification score and localization precision. It is common for keypoints to generate detection boxes with high confidence scores but poor localization, which tends to be false positives during evaluation, leading to a lower AP at a strict 3D IOU threshold. Under the traditional training strategy, all keypoints are treated with equal attention, which is the point of focus we can make further improvement. To alleviate the above false attention issue, we propose a simple but effective attention loss as the follows equation. The basic idea of the proposed loss is to assign an attention weight to each regression item in the regression loss function. For each key point, the larger the confidence score, the more attention is drawn. The closer to +1 the 3D IOU, the smaller the attention weight is. We the attention weight equation by the linear combination of confidence score and 3D IOU. Then, the softmax function is utilized to obtain normalization and nonlinearity. As shown in Table 1, we provide the results on KIT eval set on SMOKE and GUP-net. We can see that the original baseline's performance is largely boosted by applying our methods. For instance, we improve the average precision of SMOKE with ResNet 18. ResNet 34 and DLA34 backbones by +3.38 +3.44 +3.34 on moderate level respectively. Besides, our improved GUP-net with DLA34 surpasses the baseline under easy, moderate and hard levels respective +3.08 +2.85 +2.33 in AP3D and by +2.87 +2.12 +2.04 when using AP-BEV metric. We further show the results of pedestrian and cyclist on the validation set in Table 3. Our improved SMOKE outperforms the baseline by +3.14 +2.75 +2.98 on AP3D for pedestrian and +0.84 +0.86 +0.86 on E3D for cyclist, which we evaluate the proposed innovations on KIT test set using SMOKE and GUP-net as two base detectors. Table 4 shows the quantitative results of our method and other top performance detectors from the official KIT leaderboard. Overall, our improved model achieves superior results over all two bases across all settings under fair conditions. For instance, the proposed method improves the AP3D of SMOKE by +1.70 +1.21 +1.18 absolute improvements under easy/moderate/hard setting. Meanwhile, our approach increased same metric of GUP-net from 20.11 14.20 11.77 to 23.58 16.20 13.56, which is absolutely remarkable. In addition, the modified GUP-net achieves the second best map among all the competitors in the KIT monocular 3D object detection. ranking the first place over the methods that do not rely on external data. We compare the GUPNet baseline with its enhanced version with our proposed modules. As can be seen from Table 5, our method achieves superior performance improvements in MAP and NDS, which improves 1.5 and 2.4% over the GPUNet baseline, respectively. Which verifies the effectiveness of our designs on large-scale datasets. We conduct ablation experiments to verify the effects of our proposed LightFPN module and attention loss. The SMOKE 32 with DLA 34 is selected as the baseline. We add the proposed methods one by one. The results are shown in Table 6. The RIV plus LightFPN outperform the baseline by plus 2.61 plus 1.84 plus 2.59 on AP3D and plus 2.43 plus 3.26 plus 1.20 on APBEV with a comparatively higher frame rate, which indicates that our proposed LightFPN module managed to improve algorithm performance in an efficient way. The results of plus attention loss achieve superior results over the baseline by plus 2.56 plus 1.98 plus 2.55 on AP3D R11. Furthermore, the combination of LightFPN and attention loss improves the results of plus LightFPN by plus 1.94 plus 1.50 plus 1.38 in terms of AP3D and plus 2.92 plus 1.81 plus 1.78 on AP3D. Which verifies the effectiveness of our proposed attention loss. To better explain how attention loss and LightFPN improve detection quality exactly, we include an analysis with performance curves and an analysis at what distance detection errors have been reduced. As shown in Fig. 4a. The improved GUPNet with LightFPN outperforms the baseline by 20.72% relative improvement in AP3D for objects nearby and 79.56% for distant cars, which proves the effectiveness of our proposed LightFPN in multiscale detection. Then, according to the PR curve in Fig. 4b, our improvement with attention loss tends to achieve more obvious precision improvements at the low recall levels, which implies that our attention loss manages to guarantee high confidence objects with consistently better bounding boxes. To certify the effect of hyperparameters in classification loss, we perform ablation experiments with different alpha and beta combinations. As shown in Table 7, the best performance is acquired when alpha is 2 and beta is set to 4. For the sake of certifying the impact of different hyperparameter gamma in the total loss, we carry out the ablation experiments on attention loss with different gamma values. As shown in Table 8, the inappropriate proportion of term in EQ, 5, too big or too little, fails to achieve great performance. The trade-off between confidence score and 3DOU when gamma is 0.5 gets the relatively best performance. To study how many levels of feature representations are requisite to pool, 1, 2, or 3, in LightFPN module. An ablation experiment to show a comparison between different methods polling from a different set of layers is shown in Table 9. Each downsampled feature maps, times 4, times 8, and times 16, is effective for bounding box regression. Combining all three different feature layers, we manage to achieve the optimum performance. To validate the efficiency strength of our proposed LightFPN, we conducted ablation experiments to compare the classic FPN with our design. As shown in Table 10, plus FPN improves the accuracy of SMOKE 32 baseline by 2.29%, but the latency decreases from 80.80 fps to 69.25 fps. On the other hand, plus LightFPN achieves similar detection accuracy while maintaining a higher frame rate of 88.57 fps, surpassing the plus FPN by 19.32 fps. To further bolster claims regarding the lightweight design of LightFPN, We comprehensively analyzed and compared the original regression head and regression head plus light FPN in terms of parameters, floating point operations, flops, and latency. As shown in Table 11, the comparative data suggest that regression head plus light FPN significantly reduces the parameters by 89.6%, flops by 99.7%, and latency by 75.2% compared to the original baseline head, thereby validating the lightweight nature of our proposed light FPN. Moreover, the divergence between the percent movements in latency and flops can be attributed to the additional sampling operation on keypoint locations. To verify the robustness of our proposed methods, we conducted comparative experiments with noise attacks applied to the input image. The noise is set as gamma transform to simulate diverse lighting conditions, where the hyperparameter gamma follows normal distribution. As shown in Table 12, the Acura smoke baseline degrades by more than 50%. In comparison, ours maintains more than 60% of the original performance, proving our design's superiority in terms of robustness. Qualitative results of smoke with DLA-34 backbone and its improved model integrating our proposed methods are displayed. All data are from the validation set of Kitty. For better visualization and comparison, we visualize all the predictions in the form of projected 3D boxes on the plane and 2D rotated boxes on bird's eye view. Point clouds are only for visualization purposes. The comparative figures demonstrate that our contributions can improve the performance of smoke in various street scenes.